Good afternoon, everyone, and welcome to today's webinar on CFD for pump design. My name is David. I'm going to be your host for the next 20 to 25 minutes, so it's going to be really a very short session. The idea is to give you a feeling for how CFD in general, but and SimScale in specific, can be used to help you in designing pumps. A few technical notes first. We're using GoToWebinar to stream the session today, and we're going to record this session. So I'm recording it right now. The recording will be sent to everyone afterwards in case you want to review anything or forward it, so that'll be available. The second thing is that it allows for asking questions. So there's a little device, a little button where you can raise your hand or post a question. So feel free to use that. Just ask at any point during the webinar whatever you want to ask. If we have time by the end of the session, I'm going to try to cover the questions that I can answer. And if we can't answer all of them, there's my email address also in the details of this webinar, so feel free to reach out. And again, it's either me or another CFD engineer here at SimScale is happy to jump in and answer the question. All right, so let's dive into it. To manage expectations, a quick agenda, sort of what will be in this session today and what not. What we'll not cover is, the details and theory of turbomachinery, the details and theory of turbulence theory, final volume method, CFD, etc. So we won't. We'll look a little bit at general, design parameters of pumps. We're going to look at this centrifugal pump that we're seeing here, but we'll not go into, details of such a simulation setup. What we will do today is I want to give you a very short and crisp walkthrough of how SimScale can be applied in pump design, how customers are using it today. We try to use a relevant geometry here that's close to what several customers are doing on SimScale. And so we're going to, just that by the end of this session, you have a rough idea how SimScale may help you in designing such devices. A few notes first. This is we'll look today at such a pump, a different impeller here, but we basically look at the radial pump today and going to use it as a good example for how to apply simulation. And I find it fascinating. I found this fact on the Department of Energy website, where it's posted that pumps, so it's not just the centrifugal pumps, but all sorts of pumps worldwide, one way or the other, consume a huge portion of the global energy. And so every percentage efficiency that we as engineers and designers improve such a pump will have a huge impact, right? So I find this very motivational or a good note to start this webinar today, that it really matters, this kind of design work. And for that matter, I think it's SimScale and CFD in particular is best shown when we actually put ourselves into the shoes of a designer or engineer that is in the middle of a design project. And so what we're going to look at today is this little centrifugal pump, right? For whatever application it's being used, for whatever fluid it's being used, I think it represents well the design challenges that engineers and designers face when designing such devices. And so what we're going to look at today is the typical sort of questions that you ask yourself when designing it. So first, we're going to look at the outlet blade angle, right? One important design parameter of centrifugal pumps. What is the at the trailing edge of the blade? What's the beta tube, so our outlet angle, and what impact does it have on the performance characteristics of this pump? And we're going to do a little parameter sweep, look at different design, at different of these angles and what effect they have. Second, we're going to look at the number of blades. I found a nice paper that covers that, and it's really like an active area of research. Sort of how many blades do I want my impeller to have, and how does it affect the performance characteristics of a pump? Last but not least, we're going to we're going to look at how to plot the classical performance curves of a pump, so efficiency over flow rate, and to predict the best efficiency point, where it is, and what's my pump head at the best efficiency point. Before we do so, a quick overview, why now simulation, right? Obviously there is some analytical, everybody that has heard, the theory of turbomachinery, there's some analytical formulas or equations that you can use to predict these numbers, right? You can predict, you can also hand calculate the performance characteristic of a pump. And what simulation basically allows you to do is taking that to the next level, right? Taking all sorts of friction, all sorts of recirculation areas, even cavitation, etc. So really doing a full 3D analysis of how your pump will perform. And why we should do that is it's basically quickly shown on this slide. So a traditional design process of a pump without using simulation always requires you in the beginning to have a significant time spent, on your initial design, making sure it actually works or you're confident in it, build a prototype, put it on a testing stand, and then measure the performance curves of the pump. And whether or not this is sufficient for the requirements you have for this pump. Now, simulation, or CFD in particular, allows you to do all of that virtually, right? So you have a rough initial design draft, doesn't need to be fancy, doesn't need to be ironed out. You quickly, and we're going to see it later, you quickly drop it into SimScale or in simulation software. You predict the performance characteristic virtually, which allows you to do or to make design decisions earlier. And by that, save time, and that's ultimately money in your bank, makes a company competitive, right? That's just as a quick motivational note, why to care about CFD. Now there's a ton of simulation software out there, so why another one, right? Why SimScale in particular? Why should you care about SimScale? Why should you spend these 20 minutes listening to this? What we've tried to build with SimScale is a simulation solution that comes with these three main characteristics that we saw missing in the market. The first one is accessible. We're going to see it in a second. SimScale is a web application. So there's zero install. There's nothing to download. There's just a web browser that you need and an internet connection. And I know from the audience that some of you are already SimScale users. Some are new to it. So some of you might be already familiar with it. For some it might be new, so I'll cover that just quickly. Cost efficient, SimScale starts with it entirely for free. So if you want to practice it, if you want to learn it, if you want to use it for a hobby project, there's a free community plan that allows you to run simulations publicly. If you want to go private, there's professional subscriptions and where you can book the computing quota you need, so you always pay for what you need. Last but not least, it's for everyone, right? We wanted to make SimScale usable for engineers and designers that do not have a dedicated education in scientific computing or in CFD. So there's lots of unique things we built around the community aspects. So there's tens of thousands of engineers in this community that you can tap into. There's a real-time chat to our application engineering team where you can chat with engineers. There's novel collaboration opportunities on SimScale capabilities where you can simply share simulation projects with the support in real time, and people can collaborate with each other. So it makes it much more consumable, usable for engineers and designers that do not have a dedicated simulation background. For this project in particular, what we're going to do today is we're going to look at this example, right? That's the radial pump we looked at, and the workflow is always the same. You bring in your CAD model, you either import it from a cloud-based CAD tool or you upload it from your local CAD system. There's multiple formats supported. You bring it into SimScale, and then it's a web application. You can see this is a Google Chrome browser, right? So it really runs inside your browser. You then have everything you need to set up the simulation in the browser. You run it in the cloud. So all the heavy lifting is done remotely. You have unlimited computing capacity, and then you do a post-processing and look at the results of your simulation and make the design decisions. So the concept is really, you bring you come with your CAD model and you leave with the design decision. Everything else is handled inside SimScale. Just two more slides generally about SimScale. It comes with various fluid flow capabilities or fluid flow simulation capabilities. The most interesting, what we're going to look at today is, let me quickly use this drawing tools, is sort of, we're going to run today an internal flow simulation, single phase, turbulent, steady state with rotating zones, right? That's what we're going to do today. But you could also, I mean, that's basically here in the lower left, right? This is another, that's a compressor. So not a centrifugal pump, but I mean, it's also some type of turbomachinery here in the lower left. Erase all drawings. And then, sorry, let me quickly, normal. And then on the top left, we can see an external aerodynamics analysis of a car. Here in the top right, we can see a multiphase flow simulation where we predict, here we have air and water being simulated at the same time, free surface flow. And in the lower right, that's a thermal comfort analysis. So convective heat transfer is being modeled in here, and it goes down to conjugate heat transfer, etc. Everything within one product. The idea behind SimScale is having multiple types of physics within one product. So beyond CFD, there's also a fully fledged FEA capabilities built into it. There's other thermal analysis types such as conduction that you can see here in the lower left, and then also some more exotic simulation types, like here a bulk flow material. All right, but enough for the general words about SimScale. Let's directly see it in action. And for the first sort of little study we want to do is taking a look at how the outlet blade angle choice affects the or has an effect on the performance characteristics of the pump. Looking at centrifugal pumps, there's three different kinds, right? Forward-facing vanes where we have the outlet blade angle being larger than 90%, where this is being shown here in the lower left, where the head increases with the volume flow through the pump, right? So the energy being consumed by the pump with higher volume flow is basically grows unboundedly, which makes this an unstable or not robust, not stable pump. Then radial vanes, beta is 90 degrees, where the head stays the same, and then arguably the most used sort of type of centrifugal pumps in industry is the backward-facing vanes, where we have beta smaller than 90 degrees, where head decreases with higher volume flux, right? So robust, stable pump configuration. And we're going to look at this one. And that's the angle that we're going to, that's the design parameter where we're going to, in this scenario, thinking about, okay, how to choose it. So how does, for my given pump requirements, what is an intelligent choice of the outlet blade angle? And for that, what we're interested in is we're going to run three different simulations. So we're going to look at we're going to fix the parameter of the number of blades. So we're going to look at 8 blades. We're looking at 550 cubic meters per second flow rate. So this is our Q. We're looking at 1,500 rounds per minute impeller rotational speed, and at the outlet, we're going to apply simply a gauge pressure of 0 pascals to make it simple. And again, just to highlight this one, so that's you can see the different angles here. That's the important parameter we're looking at, right? And so just to give you a feeling for how this is now being modeled in SimScale, I'm going to quickly exit. Oh, wait, no. I'm going to quickly jump over to SimScale, and just for you to get a feeling for how SimScale works. Let me quickly log out here in case you don't have an account yet. What you basically do to use SimScale is you go to simscale.com, and in the top right there's a sign up button where you can create an account, and after you've created such an account, you can log into SimScale in your browser. So I'll do so quickly. The first thing you'll see after you're logged into SimScale is your dashboard. And in the dashboard, basically, it shows your latest projects and with a simple click, you open up your project. And what we're going to do, quickly jumping back to the presentation, what we basically did in this project is we uploaded 3 different configurations of this pump with these 3 different outlet angles, right? So simply in our CAD software, we created 3 different configurations and uploaded them to SimScale. And so the first one, and now this is the SimScale UI, and now you can see that this is my first geometry here, right? Pump, 13 degrees, 8 blades. This is the geometry that I uploaded, and now in SimScale, you've got everything you need to put together a flow simulation of this. Let's quickly review this geometry a little bit, that you get a feeling for what's inside here. Remove this stuff as well. And then we're going to remove the rotating region in here, right? So here I've got my impeller in here. I've got the volute, the flow volume around it, and then I have one part, and this is this cylinder part. This describes the rotating region around the impeller. And then the next step I'll do is I'll put together the simulation setup, so the physics of a simulation. I'll not go into details. I'll just give you a rough walkthrough of how such a setup looks like. So this is basically after the mesh generation was completed. There's multiple meshing algorithms within SimScale that I can use to generate a computational grid, depending on what analysis type I'm doing. And here we can see the little cells being in here, right? And then if we'll make a quick walkthrough through one of these setups for you to get a feeling. The first relevant setting is here, the type of material, so the type of fluid I chose, right? So in this case, we're simulating water as as shown in the presentation, and we applied water to the entire domain, right? So you can see that here in everything that's highlighted in blue basically will be water. And then the next relevant setting is my inlet condition. So at my inlet that I can see here, I specified 0.18 square meters per second, which is 500 no, that's not true. That's which case it is? So that's a bit more. So that's I think 600, something like that, cubic meters per second per hour volume flux through the pump. At the outlet, as discussed, I applied gauge pressure 0, and then at all walls, I'm applying a no-slip wall boundary condition, right? And now the interesting piece is over here. That's the rotating region where I applied my angular velocity, so the rounds per minute translated to radians per second, and then that's basically it, right? These are all the settings that we discussed over here. So 8 blades, 1500 rounds per minute, 550 cubic meters per second. And the last thing I'll do, and I'll not show that now, is I run it in the cloud. And just to get a feeling for, I ran that on 16 cores. So I ran it on quite a computer, and it took a little bit north of 2 hours to run the simulation, right? So this is heavy lifting. All right. So let's jump back to the presentation to review the results. And I hope you got a feeling for the I hope you got a feeling for the UI of SimScale a little bit. As I said, there's many tutorials, there's many in-depth training classes. So today is really just for you to get a feeling for how the UI works, for how the product works. But the workflow is always you bring in a CAD model, you generate a grid, and you then run set up the physics, set up the simulation inside the application, and run it in the cloud. Maybe that's a good point to quickly make a quick break and take a look at that if there's any urgent questions. Okay, there's maybe one question where it would make sense to directly address it. One participant asks, can you explain shortly the pre-processing you did to the CAD model and how to prepare the CAD model for the simulation? And that's done. That can be done easily. Let me quickly bring over SimScale here again. Um, you should see now the UI again, right? So how this model is prepared is that basically one solid, this is the outer solid that we're seeing here, right? That's the flow volume. So that's basically the negative volume of my pump. And if we basically hide this now, what's now left in here is the impeller, right? So the impeller is inside the flow volume. So it's basically these two parts, flow volume and impeller. And to apply a rotating region, the only thing that I did in addition is I added basically a region around the impeller that defines the rotating region. So as far as I know, rather standard in many different CFD softwares, right? That there's a rotating region around the impeller. And this is the region where we're going to apply the angular velocity to. I hope that answered the question here. All right, jumping back to the presentation. So what we've done is basically we set up the same simulation for 3 different CAD models, fixing number of blades, fixing rounds per minute, speed, etc. So the only parameter that we've changed is beta 2. And keep in mind we fixed the gauge pressure at the outlet of the volute. So here everywhere pressure is 0, right? So that guy here. And so what we can now see is the first thing that gets obvious is that pressure at the inlets is basically the lowest for the 33 degrees beta 2, and then it goes higher to the 13 degrees, right? 33, 23, and then 13. And we can see that the pressure increase across the pump significantly rises with rising beta 2, right? And it's not just, that's obvious for a pump designer, that's clear, but the core question is how much does it rise, right? And in addition, with different angles, the flow characteristics, the flow field inside the pump also changes and might have an effect on the performance. And so that can be now seen deeper in a cut section through the pump, right? So we can see again here that pressure increases from the inside of the impeller to the outside, which is what we expect, and we can see again the difference in the color fields, right? On the left, we have a rather low increase. On the right, we have a high increase. And then velocities, keep in mind, it's the same rotating speed of the impeller, right? Rounds per minute are fixed. And so we can see now a color plot or a color map of the velocity fields. And we can see on the right, it's the same color map for all 3 designs. We can see on the right that that speeds are much higher, and now we could, go into details and look at the trailing edge, at the leading edge, etc. But we won't do that right now because I'm shooting for 30 minutes here, and we're already running out of time. To put a number on this, if we compare the 3 different designs, and particularly the 33 with the 13 degrees design, we can see that the pressure increase is 90 kilopascals, right? So the head is significantly higher for beta 2. Again, this might be, a hand calculation might have also revealed this trend, but not in that accuracy, right? And yeah, that's sort of the first study on the blade angle. We're going to do the same now with fixing all other study parameters and only changing the number of blades. And I found this, there's a nice paper that sort of states that many parameters of centrifugal pumps are actually well understood, but the number of blades is not, which I found interesting. And we're going to use that as a motivation to quickly, jump into our CAD software, quickly change the number of blades. On the left, you can see 6 blades, then over to 8, the one we already simulated, right? And then to the right, 10 blades. And we're going to do the exact same mechanism again, right? We bring these 3 models into SimScale. We set up the physics, we set up the mesh, we run it in the cloud, and look at pressure increase head over these 3 different designs. 6 blades, 8 blades, 10 blades. Keep in mind, gauge pressure at the outlet is fixed, and we can already see again the trend, right? We can see that on the right, the inlet is dark blue, on the left it gets light blue. So we see this trend that pressure increases with number of blades, at least across 6, 8 to 10. Again, the cross-section reveals the same trend. We can see lower pressure in the middle, so pressure increase with 10 blades is much higher. Speed, velocity also, velocity field also visible here. Right? We could again dig into the trailing edge, leading edge, and go into more detail of this analysis. Putting a number at this, we're going to increase it by north of 40% if we choose 10 blades. Again, quick analysis, 2 hours computing time on 16 cores, so a couple of 100 core hours, manual time, not a lot. Sort of this quick what-if scenarios possible with SimScale. Last but not least, in the last 5 minutes of this, because I mean, it's good and nice if we're having more head of the pump, if we increase our pressure, but then again, we can also expect the torque the engine or the motor needs to bring or needs to supply to deliver that pressure increase, right? So the last quick study that I wanted to show is also showing that you can also predict the performance curves in detail. So basically run the pump through its through different volume flux, and then taking a look at efficiency, taking a look at head of the pump, so typical curves we know from classical pump design tasks, right? For that, we want to compare 2 different pump designs. So we ended up saying, okay, the 33 outlet blade version seems to be the right one, again, for our application. Might be not the right one for another one. The idea here is not to say, hey, that's the best pump, that's the worst pump. It's rather, it highly depends on the requirements, right? I just want to give you a feeling for how SimScale can be used to quickly evaluate such performance characteristics. So we ended up saying 33 beta 2, that's the one we're going to go for. 1,500 rounds per minute. We're going to look at different flow rates because we're going to look at pump curves, right, at performance curves now. 0 pascals gauge pressure at the outlet. And we're going to compare 8 blades to 10 blades. And now we want to see the complete pump field. So doing the same thing, right, dropping it into SimScale on the same geometry, on the same mesh, we simply quickly change the flow rate that goes through the pump, and we plot pressure difference across it, right? And we can immediately see, again, what we would expect. We already saw that at 10 blades, the pressure increase or the pressure difference from inlet to outlet is higher, right? And we can see that now over the entire flow rate. Then here, an interesting thing we haven't looked at yet is what about energy consumption? So what about torque, right? As expected, the 10 blades to bring this more energy, the more pressure into the fluid, we expected that the torque must be higher, right? And so we can see that with higher flow rates, the torque increases for the 10 blades more than it does for the 8 blades, right? Something we would also expect. And now we can put a quantitative number at it. And now the number that that pump designers most often care about, right? That's the efficiency plot. So over flow rate, what about energy that I put into the pump and energy that I get out of it? So what's the ratio? What's the efficiency? And we can see that, and that's interesting, is that the efficiency of the 10-blade pump is slightly higher across most of the flow rates than for the 8 blades pump. Keeping in mind that also the total amount of energy we would need to supply is higher, right? So it's not like that we found the best pump. It's just like that we can really understand its performance characteristics. Best efficiency point seems to be here, roughly at north of 400 cubic meters per hour for both pumps, for both pump designs. And if I plot this over the head curve, so head over flow rate and efficiency over over flow rate, we can see that at this best efficiency point, we would have a head for the 10-blade pump of a little bit north of 28 meters, of the 8-blade pump a little bit north of 26 meters. Right? And with that, we've basically not just looked at different studies, different design parameters, but also ultimately predicted a full performance characteristics of two pumps. And all of that, again, using a web application, right? Having all of these analysis in SimScale, inside SimScale. I am 1 minute over time, so I'll quickly wrap it up here with a quick summary. And then I look at if we will make 2 minutes more and look at the questions we have and if I can answer a few of them. Basically, to wrap this up, all of this, so the entire analysis, right, going through 3 different blade angle configurations, 3 different number of blades, and then going through the entire, what means the entire, like different flow rates, volume fluxes, to plot the performance characteristics of 2 pumps. It took roughly 30 simulations, right? Roughly 30 simulations. And to set this all up, to do the post-processing, etc., a couple of hours manual time, a couple of hours of computing time. And the reason why it's just a couple of hours of computing time, but 800 core hours, is that in SimScale, you can do all of this in parallel, right? So for example, to run these analyses, what I do is at this point, let me quickly draw something here. So to predict this point, you say, okay, all of this is one design, all of this is one mesh. So you basically have the same simulation and run it 1, 2, 3, 4, 5, 6, 7 times. And so you quickly say, okay, my Q is the following flow rate. And you send it off on 16 cores and it's going to compute for 2 hours, right? At the same time, like 5 seconds later, you're going to kick off the next 2 on additional 16 core machines. The next 2, etc., right? So you have all of these simulations running in parallel on 16 cores. And during the simulations, you have, I don't know, like 200 cores computing for you, right? A hardware or an amount of hardware that you don't have under your desk, and get all of these these values back simply in a shorter amount of time. That's sort of where the cloud simply makes you more productive, right? So this is why 6 hours computing time, but overall 800 core hours being consumed in parallel. Return, I mean, again, doesn't mean that now the 80% is awesome. It depends on your requirements, etc. But we could quantify what the blade angle of an effect it has on my pump characteristics. Also blade count. I could predict the detailed performance characteristics over the entire pump field. I can predict best efficiency point and ultimately end up in design confidence, right? And that sort of hopefully sort of conveys that with a little bit of investment, there's quite a return you can get, which is, I think, unique to such a cloud-based approach to CFD. I think I explained that, right? On SimScale.com, you don't need to take my word for it. You can just test it yourself and just create a free account. And there's many examples. There's many public projects. In fact, this project is also public, so you can simply search it in the public library, so you can take a look at it in detail. And with that, thank you very much for the attention, and I'll quickly look at if there's some questions that I can quickly answer in the remaining few minutes. Yeah, one registrant says that that looking at this, that the blade angles and the blades don't seem to be efficiently modeled or efficiently designed, and that might actually be true. So the I oftentimes say that we're simulation engineers, not pump designers. So that it should serve the explanation, but you might be right that there's certainly room for improvement in this design, which we've seen, right? So I couldn't agree more with that statement. One registrant asks if this type of rotating simulation can be done in a reverse, so to not simulate a pump, but a turbine, and the short answer is yes. We've got also many customers that do that, and all sorts of turbines. Classical wind turbines, but also water turbines, and Yeah, that's possible. Axial, radial, etc. Yeah. One user asks, or one registrant asks, was the meshing adaptive and automatic? What kind of mesh was used? So let me quickly see, and I'll not bring it up now. You know what, we'll quickly bring it up. I have it open over here. Let's take a look at the mesh. So this is a finite volume method that's being used at the back end. So it's a body fitting mesh. So it's a polyhedral. It's polyhedral cells, and they are fitting to the body. Let me quickly turn this off, and let's make a zoom in here. Right. So you can see that that there's a few layers being inflated at the boundary, and that the rest is a hex dominant polyhedral mesh. And since it's a steady state simulation, a multi-reference method was used to model the rotating region. And for how this mesh was generated is sort of, there's quite some automation built into SimScale. So when you just say SimScale, okay, hey, mesh this for me, you're going to get a decent mesh back, but you have the option to tune, you know, how much you want to refine these edges, how much, let me switch to this guy. How much do you want to refine these edges? How many layers you want to inflate? You know, do you want to resolve the rotating region in more detail? These sorts of things, right? So you can see that, for example, the cell size in the rotating region is smaller than here in the inlet, etc. So you've got quite some control over it. It's not, so during mesh generation time, it's adaptive to the geometry, but during the simulation run, there is no adaptive, so solution adaptive mesh refinement being used. There's one suggestion from a user that says, make a template in SimScale for pump design. It will be very useful. Let me quickly just cover a quick view on a public project, right? The project I demoed to you is really entirely public. So this is the link to the public project that I essentially show to you, right? And so there's a little bit of documentation to it, etc. And then you can, as a user, so you don't even need to be logged in to see this, right? And if you have a SimScale account, you can then open up the entire project, and if you like it, you can make a copy of it, and then you can just swap your CAD models. So while this is not a, you know, off-the-shelf kind of, hey, just drop your CAD model and then you'll be good to go, you can basically build on top of such existing public projects. So I hope this sort of goes into the direction you were asking. Let me see, maybe one more minute or one more question. Yeah, maybe one question on, so yeah, just to manage expectations, there's many questions. I won't be able to cover all of them, but I'll definitely, please feel free to reach out to me. There's my email address is in the webinar credentials, and I also have a list of these questions and try to cover them afterwards. One question, a last question maybe on, is it possible to simulate two phases of water in a single simulation? The short answer is yes. The longer answer, it depends. So it is possible in SimScale. Let's quickly again open up the application. It is possible in SimScale to simulate two phases. So there's multi-phase flow simulation being covered, but the for example, there's one question regarding steam. If the steam, what for example is not possible is having phase change at the moment, right? So you couldn't model that, I don't know, the steam you know, goes beyond a certain temperature and then sort of changes its phase. So that's not possible. But inside SimScale, you have an analysis type that's called multiphase, right? And this basically allows for arbitrary combination of fluids. So you can have two, I don't know, oil and water and air, etc., and the free surface is being computed for. All right. I hope so as I said, there's more questions open. I'll try to follow up via email. And please, if it's urgent, also shoot me an email, and I'll make sure I cover them. I hope you got a feeling for how SimScale works, how it's being used by customers in the pump space. And yeah, I hope to see you soon on the SimScale platform. We'll be happy, to engage and look at your particular project. And we've got a bunch of application engineers here that are also happy to jump in. So don't hesitate to contact us. Looking forward to it. All right. Thank you very much, and take care. Bye-bye.